Hi, sir. This is D. Kushi from ITA, and my roll number is 37. And my topic for Tech Talk for DMS subject is stationary graphs and spectral emission. So let us get into the topic. The spectral representation of stationary time series. Stationary time series satisfy the following properties, that is constant mean ext is equal to nu, constant variance where of xt is equal to sigma square, correlation between two observations xt plus h depends only on the distance h. So these properties ensure the periodic nature of stationary time series. So there are some of the important properties of stationary time series which ensure the periodic nature. So the first one is mean. That is, all of us know that mean means average. So E of xt is equal to nu, and variance of xt is equal to sigma square, and correlation between two observations, that is xt comma xt plus h should always depend only on the distance h. Only on this parameter it should depend. It should not depend on any other parameters. So when it satisfies all these three conditions or all these three properties, then it is said to have periodic nature. So as you can see in the graph shown below. So now let us recall one formula. Xt is equal to sigma I is equal to 1 to k xi cos lambda it plus yi sin lambda it. So it is the equation which is used for representing stationary time series. So here lambda 1, lambda 2 and lambda k are values which are in between 0 to pi range, and x1, x2 so on xk, and y1, y2 so on yk are independent random variables. So x values and y values, these are independent random variables. E of xi and E of yi is equal to 0, and E of xi square and E of yi square is equal to sigma I square. So from this equation, we have to make sure 2 points, that lambda 1, lambda 2, lambda k, so on up to lambda k are the values between range 0 to pi, and x values and y values are independent random variables with following two conditions, that is E of xi and E of yi is equal to 0, and E of xi square is equal to E of yi square is equal to sigma I square. With this time series, E of xt is equal to 0, we can give it a non-zero mean nu by adding nu to the equation. So, by adding nu to the given equation, we can give a non-zero mean. Mean is always denoted by letter nu, you have to remember that, and variance is always denoted by letter sigma. And second one is sigma h is equal to sigma I is equal to 1 to k sigma I square cos lambda I h, and P of h or rho of h is equal to sigma h by sigma naught, that is equal to sigma I is equal to 1 to k wi cos lambda I h, where wi value is sigma I square by sigma j is equal to 1 to k sigma j square. So wi value is sigma I square by sigma j is equal to 1 to k sigma j square. So sigma j is equal to 1 to k is nothing but the value of sigma j square lies between the values from range 1 to k, any of these values. The Riemann integral. So we'll know the formula for the Riemann integral. Integral a to b g of x dx is equal to limit delta x tends to 0, sigma I is equal to 0 to n g of ci into xi minus 1. The Riemann integral for style is this. So for this we'll have another formula. So integral a to b g of x df of x is equal to limit delta x tends to 0, sigma I is equal to 0 to n g of ci into f of xi minus f of xi minus 1. If x is continuous, if f is continuous with derivative f, then integral a to b g of x df of x is equal to integral a of b g of x into f of x dx. So if f is continuous with derivative f, then the equation becomes, by combining the above two equations, you will get another equation, that is integral a to b g of x df of x is equal to integral a to b g of x f of x dx. If f is a step function with jumps pi and xi, then the equation becomes integral a to b g of x df of x is equal to sigma pi g of xi. First, we are going to develop the concept of integration with respect to stochastic process. So with respect to stochastic process, you are going to develop the concept of integration. Let nu of lambda tends to lambda belongs to 0 to pi denote a stochastic process with mean 0, that is nu is equal to 0, and it has independent increments, that is independent increments means, as I've already mentioned, the values of xi up to k and yi to k. So the equation becomes e of u of lambda 2 minus u of lambda 1 into u of lambda 4 minus u of lambda 3 is equal to 0. That is mean is equal to 0. So here this equation is written for the condition 0 less than or equal to lambda 1 less than lambda 2 less than or equal to lambda 3 less than lambda 4 less than or equal to pi, and e of u of lambda is equal to 0 for 0 less than equal to lambda less than or equal to pi, that is in the range of 0 to pi. In addition, g of lambda is equal to e of nu square lambda for 0 less than or equal to lambda less than or equal to pi, and assume g of 0 is equal to 0. It is easy to show that g of lambda is monotonically non-decreasing, that is g of lambda 1 is less than or equal to g of lambda 2 for lambda 1 is less than lambda 2. Now let us define integral 0 to pi g of lambda d mu of lambda. Analogous to the Riemann-Stieltjes integral, the equation becomes integral 0 to pi g of lambda d f of lambda. So when you compare these two equations, for the first equation, if you apply the analog of Riemann integral, that is analog means opposite, then the equation becomes integral 0 to pi g of lambda d f of lambda. Let 0 is equal to lambda naught, lambda 0 less than lambda 1 less than lambda 2, so on less than lambda n, and this is equal to pi be partition of the interval. Let delta n is equal to max of lambda I minus 1. Let lambda I denote any value in the integral lambda I minus 1 to lambda I. So now we are going to consider another equation. Vn is equal to lambda I is equal to 1 to n g of lambda I star into nu of lambda I minus nu of lambda I minus 1. Suppose that limit n tends to infinity, lambda n is equal to 0, and there exists a random variable v such that limit n tends to infinity e of vn minus v whole square is equal to 0. The v is denoted by 0 to pi g of lambda d nu of lambda. So here we are having some other properties to verify the condition of v. E of 0 to pi into g of lambda d nu of lambda is equal to 0 is the first property. The second property is e into integral 0 to pi g of lambda d nu of lambda whole square, that is nothing but 0 to pi g of square lambda dg of lambda. And the third property is e into integral 0 to pi g1 of lambda d nu of lambda into 0 to pi integral 0 to pi g2 of lambda d nu of lambda. So when you multiply, you will get another equation, that is integral 0 to pi g1 of lambda g2 of lambda dg of lambda. So let x of lambda, here lambda belongs to 0 to pi and y of lambda is 1 that belongs to 0 to pi. Denote an uncorrelated stochastic process with mean 0 and independent increments. Also let f of lambda is equal to e of x square lambda and e of y square lambda. for 0 less than or equal to lambda less than or equal to pi, and f of 0 is equal to 0. Now define the time series, that is xt denotes t belongs to t as follows. Xt is equal to, so now you are going to define the time series which was defined before. Xt is equal to integral 0 to pi cos lambda t dx of lambda plus 0 to pi sin lambda t dy of lambda. This is the equation for time series. Then e of xt is equal to e of 0 to pi cos lambda t dx of lambda plus 0 to pi sin lambda t dy of lambda. Again, after further solving, the equation of e of xt becomes e of integral 0 to pi lambda t dx lambda plus e of integral 0 to pi sin lambda t dy lambda is equal to 0. Also, sigma of h, e of xt plus h comma xt is equal to 0. That is e of integral 0 to pi cos lambda t plus h dx of lambda plus integral 0 to pi sin of lambda t plus h dy of lambda into integral of 0 to pi cos lambda t dx lambda plus integral of 0 to pi sin lambda t dy of lambda. So after solving this equation, it will become e into integral 0 to pi cos lambda t plus h dx lambda into integral 0 to pi cos lambda t dx lambda plus e into integral 0 to pi sin lambda t plus h dy lambda into integral 0 to pi sin lambda t into dy lambda plus e into 0 to pi cos lambda t plus h dx lambda into 0 to pi sin lambda t into dy lambda plus e into integral 0 to pi sin lambda t plus h into dy lambda into 0 to pi cos lambda t dx lambda. So the given equation you are writing into 4 possible ways, and the equation becomes like this. So further, after solving of the above equation, you will get integral 0 to pi cos lambda t plus h cos lambda t df lambda plus integral 0 to pi sin lambda t plus h sin lambda t df lambda plus 0 plus 0. So after further solving, the final equation is integral 0 to pi cos lambda h df lambda. Thus, a time series is defined as xt is equal to integral 0 to pi cos lambda t dx of lambda plus integral 0 to pi sin lambda t dy of lambda is a stationary time series with nu is equal to e of xt is equal to 0 and sigma h is equal to 0 to pi cos lambda h df of lambda. Here f of lambda is called the spectral distribution function. If f of lambda is equal to capital F of lambda, then it is called as a spectral density function. And sigma of h becomes integral 0 to pi cos lambda h df of lambda, that is equal to 0 to pi cos lambda h f of lambda d lambda. Note, where of xt is equal to sigma 0 is equal to integral 0 to pi df of lambda, that is equal to integral 0 to pi f of lambda d lambda. The spectral distribution function f of lambda and spectral density function f of lambda describes how the variance of xt is distributed over the frequencies of the interval 0 to pi. The autocovariance function, that is sigma of h, can be computed from the spectral density function f of lambda as follows. So sigma h is equal to 0 to pi cos lambda h f of lambda d lambda is equal to integral 0 to pi e power minus lambda h f of lambda d lambda. So as you all know, e power minus theta formula is cos theta plus I sin theta. Also, the spectral density function f of lambda can be computed from the autocovariance function sigma h as follows. F of lambda is equal to 1 by sigma 2 pi into sigma of 0 plus 1 by pi into sigma h is equal to 1 to infinity sigma of h into cos lambda h. So now let us look at the examples for this. let UT denotes to T belongs to T be identically distributed and uncorrelated with mean 0. So the given condition is sigma of H, that is sigma square at H is equal to 0 and 0 where H is not equal to 0. And f of lambda is equal to 1 by 2 pi sigma into 0 plus 1 by pi sigma H is equal to 1 to infinity sigma H cos lambda H. So after substituting the values, f of lambda value becomes sigma square by 2 pi if it is in the limits minus pi to plus pi. So here is the frequency graph for lambda value, that is between minus pi to plus pi. Another example, suppose x1, x2, so on xk and y1, y2, so on yk are independent random variables with e of xi and e of yi is equal to 0 and e of xi square and e of yi square is equal to 0. Then let lambda 1, lambda 2, so on lambda k denote k values in the range of 0 to pi. Then xt value becomes sigma I is equal to 1 k xi cos lambda it plus yi sin lambda it. Then sigma h value becomes sigma I square cos lambda ih. So if we define x of lambda in between lambda belongs to 0 to pi and y of lambda and lambda belongs to 0 to pi, then x of lambda becomes sigma xi and y of lambda becomes sigma yi. So the equation of f of lambda becomes e of x square lambda, that is variance of sigma xi, that is equal to sigma I square is equal to e of y square lambda. Note, x of lambda and y of lambda are random step functions and f of lambda is a step function. Another important comment is that in the case when f of lambda is continuous, then f dash lambda is equal to small f of lambda, then sigma of h is integral 0 to pi cos lambda h into df of lambda. So this is the equation. Sometimes the spectral density f of lambda is extended to the interval minus pi to pi and is assumed symmetric about 0. So it can be shown as f of lambda is equal to 1 by pi sigma into 0 plus 2 by pi sigma h cos lambda h. From now on, we will use the symmetric spectral density function and let it be denoted by f of lambda. So f of lambda is equal to, as you already know, we have derived the formula before, then sigma h becomes integral minus pi to pi cos lambda h f of lambda d lambda. So let us know about spectral density function. Moving average time series of order q. So let alpha naught is equal to 1, alpha 2, so on alpha q denotes q plus 1 numbers. And xt is equal to nu t plus alpha 1 nu 1 so on alpha q nu t minus q. So make a point that here t value is obtained from linear filter. Now f nu of lambda is equal to sigma square by 2 pi. So the equation of f of lambda becomes a of lambda square that is equal to sigma square by 2 pi sigma q s to 0 alpha s e power minus I lambda s whole square. So first example, we'll take the value of q is equal to 1. Then f of lambda equation becomes sigma square by 2 pi of mod 1 plus alpha 1 e power minus I lambda whole square. Then it becomes sigma square by 2 pi 1 plus alpha 1 e power minus lambda plus 1 plus alpha 1 e power minus lambda. So after solving this equation, you are going to get sigma square by 2 pi is equal to into 1 plus alpha 1 square plus 2 alpha 1 cos lambda. In the same way, you are going to solve for q is equal to 2 and f of lambda equation will become sigma square by 2 pi into 1 plus alpha 1 square plus alpha 2 square plus 2 into alpha 1 plus alpha 1 alpha 2 into cos lambda plus 2 alpha 2 cos 2 lambda. So these are the graphs which are used for the representation of spectral density function. So you will represent it like this. So thank you. I hope you have understood this topic.